MasterKey Retaining Walls is just one of over 30 different modules in the MasterSeries suite. Today we'll be looking at the standalone Retaining Walls program. So straight into the MasterSeries, and I have a most frequent, but for those who are unfamiliar, down to MasterSeries and into the MasterSeries icon. What I now want to do is just go straight in and do some retaining walls. So into retaining walls from the designer suite, and I'm going to choose a wall that I was working with before, and if I sort them by date, I will see that that's the one that I was working with, which is me, and just say get file. So here we go. This is the sort of wall that we're going to end up with. Quite complex, with point loads and surcharges and slopes and props, but we're going to work our way all the way up to that. We also have here layered soils and water tables. So just walking through some typical retaining walls, and as we go through them, we'll look at each one in detail and expand on how you change these things. And I'm going to go to the second one, and this is a retaining wall with a slope front and a slope back, so a tapered stem to the retaining wall. If I didn't want a stem, or sorry, a taper, I could just take that off and take that off. So everything's very, very easy. So if I wanted just a front stem, a front taper to my stem, obviously I will need to put that in. As you can see, we can easily stipulate the height of the wall. Very straightforward, and everything is instantaneous. So if I start going up in height, suddenly I get a failure. The wall is going to fail, and in this case it's going to fail on sliding. So I would need to take some more earth onto the wall to improve that. And I'll just put that back down to 3 meters. And naturally you can go in and overtype. So if it's 3.505, then you could put that value in. It's not just restricted to the simple values. And you have your toe and your heel. We then have the back soil, and we'll see here that we're sitting with a soil slope of 0. We can increase the soil, as we can see very quickly. As we add in more soil, the wall suddenly starts again to fail in sliding, as we're getting more push than we are gravity on this wall, and it's now fitting. So if I was to go up to a 10-degree slope, I would need to lengthen my base to be 2.1 heel on the wall to make that work. Now somebody actually asked me the other day, can we do sloping walls? And well, the answer to that is actually yes. I don't imagine that you'd want to slope it, but if I make that as a negative value, that then is sloping by the 100 mil. So it's a parallel wall, but it's sloping back. Now obviously it improves certain things, but not the sliding, because we now have less soil on the wall, and we would have to increase the wall length naturally by that additional 100, but maybe not quite as much as the additional 100 to make that work. So it's how simple it is to do a simple reinforced concrete retaining wall. We're going to look at the design now. So let's take off our back slope and our, sorry, I got a pop up there, front slope, so a plain wall, and I'm just going to thin that down, say to 250. So 250 wall looks to work. So what I'll ask first of all is how, if I wanted to shorten the toe, I'm going to shorten that down to only 500 projecting. How long would I need to make my heel? Bearing pressure is still a problem, and obviously we may look at the soil data at this point and decide to increase our bearing pressure above the 100 to 110, 125, 150, whatever we require. But I'm going to stay with that 100, come back to my wall data, and the only other solution is to lengthen the wall, and you have to lengthen it considerably to help the bearing. So clearly it's cost us a lot to reduce that toe. But if that's what's required, that is required. So put the toe back out to 100, or sorry, 1000, and you'll see I'll come down quite considerably now. So to 2, so 3450 on a 250 wall. I'll make that 1.5 and see if that does the job. And 1.5 doesn't work, so we'll have to make it 2.5, and then suddenly we've got our 350 wide base on our wall. We can add a nib. Nibs can be awkward is the simple question. So I'm going to put into me here a 300 deep nib, and I'm going to isolate it at the same point and make it 250 the same width, so it is now working. Now the problem with the nib is that we can take an increased passive resistance, but our active pressure increases quicker at the start, so it's actually detrimental according to the methodologies in both 8002 and EC3. So most people don't use nibs nowadays, or they put them in, and from analysis point of view they ignore them. I know there is some sort of flow net. If you did a computational fluid dynamics analysis, you would find that the pressures are equalizing a wee bit better here, and you are getting the benefits. So in my case, I'm happy to do without a nib altogether because I don't need it anyway. Now, our problem was sliding. So another solution, no it wasn't, it was, yes it was sliding, is to prop the base. If this is going to be propped off something else, we can see that sliding is still only the problem. And if I'm happy at 2.5, I will come along to my props and ties and prop the base of the retaining wall. So it won't have a sliding problem because it's propped at the base, be it from whatever reason you want. Now let's walk along to another type of retaining wall, and we're now looking at, that's the same, and now we've moved over to masonry, and in this case a 325 wall, you know and I know that it's not going to work unless it is reinforced in some way. And if we look at it, it says reinforced masonry retaining wall. If I go to the masonry reinforcement, you will see that I have in plane 12s at 125, so we're putting pairs of 12s every 250, 225, so you'd have to be working with hollow core blocks and mortaring them up to actually get that to work as little pockets. I do not like these reinforced single skin walls. They're not very, very nice to work with at all. Naturally, your other option is to go for a cavity reinforced wall. Now with the cavity reinforced wall, what you have to remember is that your block is your compression, so you want to increase the strength of your compression blocks up to something, say 17 Newton or 22 Newton, because that is your compression zone. And you will notice, for those who are not experienced, the wide block is on the outside, because again that is your compression zone. So your design, this is just form work, your design is from the center of the cavity for the rebar to this compression zone, and we will see that this works with cavity reinforcement 12s at 200. Would I get away with 10s? And I will see no, I don't get away with 10s. So what you could do, but it's probably not worth it, is put 10s at 100 in and then slip them to 10s at 200 for the top half of the wall. Might be a solution, or just keep it simple and go for the 10s at 200. So these are all in the cavity, of the wall, and we're using 500 grade steel. So cavity reinforced masonry walls. The next stage would be without reinforcement is to step it, and you and I again know that stepped plain masonry walls are a disaster. Depending on whether you've got water table behind it or not, you can be into a 1:3, even a less than 1:3 ratio on your width to height of your wall. So it's very simple to set up. All we need to do is to tell it that we're going to come down 675, out 225, down 450, out 225, down 450, out 225. So if I wanted to, I could take that out. We're back to plain and it's failing miserably, and I could even put that on the inner side. So if you were propping up where you'd excavate it under somebody else's property, you might want to go for this arrangement instead. Again, I don't like them, but sometimes needs be. They're more useful when you're doing a simple 1.5 meter high wall, but for this 2.5 meter high wall, your solution is most probably either a reinforced concrete wall, or because you're going to need the shutter behind it and you don't want to have to get that out, a cavity reinforced masonry wall. So those are your typical configurations of walls. We now come to something that's very nasty, very horrible. I don't like it at all. It's there, it's doable. What we're talking about is a wall that's masonry with counterforts. So with counterforts, we can design this wall to be a lot thinner with these little counterforts. The counterforts are 440 wide and it's 660 wide at the base, and they are at 225 centers. If I was to increase the centers, the wall fails. Now you will also notice that I do have reinforcement in the wall as well. So if I go to my masonry, it doesn't tell me much. If I go to my reinforcement, I will see that I am dealing with 6mm bars at 100. So every leaf has got a 6mm bar running through it, on this side and this side. You need it on both sides because with a counterfort, it's all horizontally spanning, but you have hugging and sagging moments, and therefore you need to work that out. You also then have the pier itself and its reinforcement. And of course we can move the pier to either side depending which we want, and that can obviously have an effect on overall stability, but also on the forces applied, and the fact the main steel is in compression rather than tension makes things interesting. Personally, I prefer to see the counterfort in here, so you have the tension steel in the pier and the wall is just doing the compression plus the horizontal spanning. So that's your counterfort walls. And then finally we come back to my crazy wall. So crazy walls, this is where we're going to get into real depth and spend a bit of time looking through the parameters that we're able to work with and use in the retaining wall program. So obviously wall data, we can see it's got 100 taper up to a 200 wide. It's got a 500 here, upstand above the soil, so we can take our wall higher than our soil, either to put wind onto or to make it such that that's the physical wall that's defined, and therefore we are able to use and define it for self-weight and for the reinforcement that's going to be required. If we then look, we will see that we actually have soil front and back, a 500 mil of soil, or is it 700? Not 700, and oh sorry, there it is, 500 of soil and our 300 thick base. So this 500 soil is obviously going to be of very little benefit to us in certain instances due to the requirements of overdig. Our water table is at 500. You'll see we're failing at this point in time quite considerably. So what we need to do, if we increase our water table, it just goes, nah, I'm not happy at all, and everything was failing miserably. And now as I reduce my water table, down to the ground, we're improving our bearing pressure. And if I pull that on down, what I would normally do is if I want to get rid of it, I go -500, and that pushes it below the base, and therefore the water table is not considered at all. So our whole soil is drained. Obviously you have to ensure that that's drained, but in this case we also have 2 layers of soil, so it very much wouldn't be the case that you'd have 2 layers of soil and drain it. You would expect to have a water table of some sort. So I'm going to put that water table back in again at 500 or even higher. High. So it's getting some annoyances when I get that water table up above that, but we'll look at that in a minute. So that's our water table. Everything else is pretty straightforward and we've talked about. In here, let's move across to the soil data. Now, obviously, we're EuroCode fanatics nowadays, and we're designing to EC7 and EC2. So we're doing a reinforced concrete wall with reinforced base to the EuroCode. You'll see we have all these mobilization factors and friction factors, and we have them for the back and the front soil. And for the back soil, we have stipulated that we want a layered, so the upper soil and then the lower soil. So in this case, the upper and lower soils look to be pretty similar, except for the upper soil, I'm going to change the soil density down to 17, and for the lower soil, I'm going to make it a more dense 20 Newton soil. So we're giving ourselves problems here. We have 2 different sets of soil. You can see the difference in the slope if we took out the point loads, and I can do that in a moment. And you obviously have your submerged and ratios and things like that. Props and ties. So props and ties, let's get rid of the prop at base, and of course then we have a massive problem with sliding. So prop at base, we can also put in props at levels, so I can put in a prop at 2.3 meters up. So if I was doing a basement, I could come in and slap in my prop at the level I require. I can also put in spring props if you're clever enough to work out, and obviously just like in ordinary structural design, spring stiffnesses are telephone numbers. They're big numbers. The number of kilonewtons to move it by 1 meter. So you would be talking something quite considerable here. We can see here the bending moment diagram being totally changed because of the physical zero movement prop here. If I was to go in and put this in at 1 kilonewton per meter, there's no change in the diagram. If I was to put this in at 100, it's slightly changing. You're looking at the bending moment diagram over here. If I was to move it in as 10,000, we're beginning to see the prop cantilever now taking effect, and we're beginning the curvature. If I go another 2 zeros, we now get our more or less, it ain't going anywhere, propping of that. So that is pretty close to being fully propped. Yep, there was less than 1%, less than 0.1% difference between that, a million and fully propped. So that's your props. I'll just take those out. We can also do the opposite. We can put a tie in, and you can put a tie at an angle. So if you have a wall you want to put in rock anchors or soil anchors and tie it up, you can do the same yourself and put the tying force. Never done one myself. So that's your props, and then we have the physical loads. You have, let's take all these off for a start. You have your surcharge. Now you have your basic 10 kilonewton load, and then we can apply an additional surcharge. Now additional surcharge is going to cause us to fail. So an additional 2.5 kilonewton surcharge. You can also put a horizontal surcharge, and that horizontal surcharge can be a 10 kilonewton load at 850 up, which is a normal handrail load, or it could be something more substantial from, and bear in mind this is the load per meter of the wall. All these loads are per meter of the wall. Or we can turn around and say, no, 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 we actually want to just have a 1.2 kilonewton wind load coming onto that and been blowing on it, just to make sure we cover everything that is applicable to this wall. So I'm just going to take that off and will not deal with a horizontal surge. So then we have the full and partial UDLs. As you can see, I've gone for a 10 kilonewton live load between 1.7 and 6.5 meters. So from about here all the way back, I'm putting in this additional 10 from construction, from a house, from whatever, although probably a line load would be more applicable. So we can apply those, and we could apply two of them and separate out the deads and the live because of the factoring. And you'll see that you do get a change in the pressure equilibrium diagram because of the surcharge and then the partial surcharge giving us a little kick and drop as it comes into play and then as applied, and then there's no more of it, so it does a relaxation. And obviously this additional soil gives us a kick as well. The newer soil takes up the resistance better. So I'm going to take off that partial UDL. But what I am going to do in this case is put on some point loads. So I can have point loads on the soil, and that's what these are at 900 and 1250 back. Sorry, 2.5 meters back from the inside face. I can also put a point load on the center of the wall. If the wall is 200 wide, I put it at -100. And then the most weird one of the lot is I can actually put a wall load outside the wall. And this is very handy if you're going to be installing pipe runs on a wall and you want to make sure that per meter run these pipe runs don't cause it to overturn, because it would be a destabilizing load in that criteria. Also, there one say if you had some sort of walkway mounted against the wall, 700 a meter wide, then you'd also want to look at that as an additional load, which is why we can also move it up and down on the wall as well. So we're able to take those very complex loads directly onto the soil. Now that's our loads covered. So what I'm now going to go and do is into reinforcement, and as you saw, we can have the C3240 concrete. We're going to go for 500B. We have all the different grades, and you can add in your own grades if you're working in Africa. I know quite frequently in Africa they're still using in some areas 425 rebar and the Y designator, whereas we're happier working with the 500B in our reinforcement. So then we have our covers and then our wall reinforcement, all very, very straightforward and easy to apply. We can also, for a concrete wall that has no reinforcement in it, we can put a tensile strength in for the concrete itself to resist that. Now, I am up to here. Let us go and look at masonry, and what I'm going to do is I'm going to come back to the very start, to probably that second one, and I'm going to copy that as a brief 12. And now I'm going to say I want to make this into a cavity wall. So I'm going to turn around and I'm going to say the wall is 300 wide. 100, 100 and 100. And I now want to make it into masonry wall. So the first thing I do is I tell it it's masonry. Very straightforward. Oh, there we go. I'm going to tell it that they are concrete blocks and that they are 10.4s, 10 Newton blocks. And I'm not going to go for any fancy manufacturing or execution classes. I'm just going to keep it simple. we've obviously got massive failures. We've got sliding problems as well. I always tell people, once you get your dimensions of your wall for your stem, you really want to, at this point in time, think of how to get your sliding resistance out. So that's when you size the size of your base. And there we go. The base is now long enough. We could possibly pull back on that because it's not an overturning issue until we get into there. So we can cut that down, and I don't think we can go any shorter. Again, it is the sloping that causes us to have such a long base, and the water table, obviously. That's our problem to deal with. We will not change it. So back to my masonry. So the next thing I want to do is say I want to have an outer leaf, and whether I want it to be just a cladding and therefore it's only carrying self-weight and no strength, or I want to fill it and make it into a composite action. So we're going to use the composite section. So now I've got 100 outer leaf and 100 cavity, and I can see now that my wall isn't working. It's 440% overstressed, and if I go to my reinforcement, I will see it's turned off the outer leaf rebar because it's a cavity, and it knows the cover to the cavity should be really 50. We'll put it in the center, so 50 less the rebar, we're going to call it 45, because we're going to work with, or even 40 just to play it. No, 45's better, it's more conservative. So we're seeing that if we want to make this wall work, we would need to either decrease the pitch of the bars, but at 500 and something we're just out of this world. We're not going to work at all. So let's look, and we'll see we've got a moment and a shear problem. So clearly we need more resistance. So in this case we need more resistance by increasing the wall. And you'd think you would just come along, and I'll just scroll up to the top and increase the outer leaf. And there we go. So 215 outer leaf. And that has automatically kept the cavity at 100, kept the inner leaf at 100, and it's just increased the overall width for you. So we're still working quite well, and I should have said that my outer leaf is not clay bricks, it's going to be concrete blocks, and that's improved everything considerably, and they will be a 10.9 block, and we'll see 10 Newton blocks. If we come back to reinforcement, we probably need a lot less than we did previously, so back to 200s. 200s is just failing and no more. So do we go for a wider cavity, so have 100 cavity, 150 cavity, which we can do, or do we go and increase the diameter of these bars, the 16s, or do we drop these down to 150 or even 175 and really annoy the steel fixture? But 175 works, and if it's a very, very long wall, it may be economical to do that. Personally, I'd rather see them at the 150s. And there you go, that is the wall designed. So again, very simple ways of generating a cavity reinforced wall. Now, one word of caution is that because we're in a cavity, we can do what we want with the reinforced wall. When we're in a pure reinforced wall, we need to keep these down to be less than 6 mil. So if I go back to one of my previous walls, which was the solid reinforced wall, which was this one. Oops, one too far. There we go. You will notice that I only use 6 mil bars for the longitudinal at 225, so intervaled at every other brick course. So if I went up to 8 mil bars, it actually gets annoyed because the maximum distribution bar in a mortar bed is 6 mil. So I'm going to drop that down to 6 mil again, and it's all happy. So the last thing we need to look at before we look at output is highway loading. So coming along, we've done that one, and now we're into reinforced retaining wall highway loading. So it's a highway adjacent to a highway. We're using the highway loading rules to design this wall, and we'll see that it is failing on sliding. And of course, all we need to do, as you know, to satisfy sliding is increase the heel length, and then we need to satisfy the inner reinforcement. So go to reinforcement and 12s, wrong way. Oh, fussy boy. 12s at 100, that's a wee bit much. What about 16s at 150? 16s at 200. Make those all 200s as well. Nice and neat. Probably would I need 16s in the base? Actually I do. Do I need them in the base? No, I don't. So the bottom could be 12s and then 16s. So, and we could then readjust that back down. I would have thought 150, 200 would be good enough for those. There we go. So that's our highway wall. All we had to do is ask to do a highway loading to the BD 3087 and 3701 in our design. We also can do the more complex highway loading where we actually ask to do a bridge abutment, and we're able to apply our loading on our bridge abutment and stipulate whether it's an HA or an HB load, whether it's a footway load, an accidental wheel load, a longitudinal, a dead steel, dead concrete. We can stipulate which of the different conditions that we're using for each of our individual loads. If you come back to your main loads and you apply this, you will also see that it's interested in what it is as an HB and HBR construction load for your design, because that will affect its load parameters in the highways. And yes, of course, we are now filling again in our retaining wall because we need to increase our length. One of the few things people don't notice is that we are able to put in two different bearing stresses. If I was to go to one of my full EuroCode designs, possibly that one, and you'll see that it's the back pressure. Now we are assuming M1 and M2 are using the same bearing pressure, but if your circumstances require, you could judge to use them at different instances in each of the M1 and M2 situations. So you can have the two bearing pressures. The other thing we do is we have the back and the front bearing pressures the same. If you leave that, so they're all the same, whereas I could increase the bearing pressure here and decrease it there, or vice versa, depending on what I'm finding in my design. Naturally, those are really set as limits at which point we show you a failure in your wall, your bearing pressure. So that's of note. So if I went up to 200, so if I was bearing onto rock, I would find that, or very, very stiff clays, that with a 250 bearing pressure, 225, we don't have a problem with this base in that respect. We do have a little problem with the length of the base is too little and under pressure, so we're just getting, in certain loading cases, too little of the wall under positive pressure. on the wall. So we do have that. Obviously, the things that we never really, as engineers rather than geotechnical people, touch are things like soil cohesion. So if I was to go right the way back to one of my initial walls, I can turn around in this and I can say that I actually have, my back soil has a cohesion of 20, and suddenly that increases because the weight sticks to the wall and pushes onto the base, and it causes us to have a higher pressure. And likewise, we could in our base turn around and give ourselves a cohesion more frequently on the base. Very limited cohesion would be, and the cohesion in the soil itself is just for working out this angle of friction and things like that. But put that back down to 0. But we will find that a cohesion in the base will improve things considerably. So we have all these parameters in the soil that we can play with. We can also do earth pressure at rest, and of course earth pressure at rest is more onerous because the active pressure has relaxed some of the load, whereas at rest you get a fuller load onto the wall. So we have these options here again to use earth pressure at rest, and at which point stability is okay, but reinforcement does need to suddenly jump up to 16s at 200 in this example. So that is all the scope of using the software. Very, very detailed, very comprehensive, single standalone program for using with retaining walls. Output is superb. If I go and I print everything, even though some of them are failing, and I'm going to send it to my PDF writer, and yeah, I'll print, I don't know what my logo is, but I'll print my logo, and off it goes, and it's going to spit all those out to the printer, and we have at the moment 12 retaining walls. 12 retaining walls give us 29 pages. So if I just close that down and just save that, and I'm going to save that to my desktop and replace the old one, absolutely, always do. So we have our retaining wall, and all the calculations that came with it are all coming out for that. So that's your output. You also have the facility to export your walls, and you would export these one at a time. So I'm going to export this one as a DXF, and I'm going to assume that I'm going to use U-bars and straights for the walls and the base and the tops. I'm going to assume I'm 7.5 meters long, and I want the wall kicker, that's how high up I go before I start my lap length, to be 250, keep it out of the muck. And I want my minimum laps to be 500. And we're going to go for a drawing 1:20 scale, and I'm going to go for 3mm labels and dimensions 2 mils. And I will just export that straight out as an export, and it's now going to throw in AutoCAD for me. And AutoCAD has just come up on the other screen. And here we go, it's come back onto my screen. So there we go, my initial retaining wall with the front elevation and the plan view. I also then have the ability in here to create a schedule that matches that. So that is my reinforcement that I require, including all my distribution steel, as well as there's my distribution steel for my wall. And I can come along and I can say, well, what was the weight? and we'll see that it's 1.345 tons of steel. So that's all part of the program. You can also export to our RC detailing package, Master RC, and then put additional notes onto it if you wish. And you can export to something called PowerPad. If I was to export, if you have our PowerPad software or our calculation wizard, you could export to a Word document to annotate the information, and it's just thinking about putting up the data, and it's just writing on my other screen. I will pull that across to you in a second. It's just finishing off the output, and then we shall look at all the questions. Are there many questions? Oh goodness gracious me. And it's still outputting. So while that's doing that, I'm thinking about it. Here it comes, done. So there's my output into, because I had the additional little program for exporting to Word, I have my title block with all my calculations in my design, and that's all nice and neat. I'm not going to save that. So there are two versions of PowerPad. Sorry, two versions of the retaining walls. There's the full version, which I've been demonstrating, and then there's a smaller version that is available with PowerPad. And you can obviously, if you have the PowerPad version, upgrade to the full version at a discounted rate. So back and let us look, and which face is the inner and which is the outer? Reasonably easy, in that the inner face is the face against the soil. It's the right hand face, and the outer is the one that's open to the air usually. Weep holes. Is weep holes there? Weep holes are part of your own specification. If you've got a water table, you're probably not going to be putting weep holes in, other than maybe one up above. If you have it fully drained, it is really up to you to put the weep holes in and have it such that it's filtered and the water does get out. And obviously, if you're drained, you have to be able to drain it way back to here, otherwise your virtual back is also a problem. To start, it assumes a surcharge is 10. Yes, it does, but you can override that. Defaults, the minimum surcharge 10, and the EuroCode has a similar criteria. So you can override that. Is crack depth considered? Yes, it most definitely is. I mean, cracking of the soil is, to me, the most scary thing. People think that they drain everything, but if you shrink back and it freezes or anything, and you cause a gap here, certainly you're going to get water up that 1 millimeter. But and put a pressure on it. But we do also have the facilities to do the cracking, and I'm just looking at soil data. There we go, tension crack depth for the back soil. And if I said I had a 500 deep tension cracks, then that adjusts everything down, because then the water table's below that in the first place. But I always get nervous, thinking about not having any water here at all. It's just my cautious nature. But just take that back off. So yes, tension decks. Somebody's asking, and it's a very good question, Gary, can you restrict the bar length in the scheduling? That is, when we go to export, to 6 meters. Well, the simple answer to that is, obviously for the longitudinal steel, you detail it for a less than 6 meter length. For the other bars, you just would make sure you're using new bars to make sure that none of your bars' overall lengths get bigger than the 6 meters. I know Gary's asking that because he's based in the Channel Islands, and rebar only comes to site or comes to the Channel Islands as 6 meter lengths. Interestingly, it comes as a 12 meter length bent in two, like a big hairpin, but obviously they have to cut that wee bit off because it's just been deformed bad. What depth of accidental excavation is included? Good question. The accidental excavation, or overdig as I would have called it, is 500 mil. Now in the EuroCode I believe also that there's a percentage of accidental overdig. I think it's 10%, but a maximum of 500. So it used to be you got penalised when doing very small walls with this 500, whereas nowadays, thank goodness, you can take it. So in this case of a 3 meter wall, you could argue it's 300, but it's actually on this side here that you're taking off 10%, so it's only that 50 mil that you're actually taking off from the 500 on that. Can you apply non-uniform? You can apply non-uniform in that you could apply a series of increasing or decreasing point loads at meter centers, or you could apply a series of 1 or 2 meter lengths of partial loads, but they are, in essence, each load itself is either a point or a uniform load. So we can't do tapering. So ladies and gentlemen, that leaves me to do a quick recap on where we were on the PowerPoint presentation, and that's the button I want. So what have we seen today? We have seen design to the British and the EuroCodes as well as the Irish. We've seen concrete and masonry, and we've seen cavity, bed joint and pocket reinforced masonry walls. We've just seen design to EuroCode 7, 8002 and good old-fashioned CP2, and highways to the 2 BD documents. We've looked at stiffened and unstiffened walls, buttressed or counterforted, and layered soil materials. And we've looked at cohesion and granular soils, sloping backs and fronts, upstands, at rest. So we have looked at a lot of details. So what does this all give you? It gives you a powerful and flexible program, and obviously being modular, you only buy what you need. If retaining walls is all what you need, that is all you need to buy. You don't need to buy the full suite. And all the different programs in this suite are all similar, and it makes it easy to learn and through this common user interface. And as you know, all our existing users will tell you that we're a very proactive company with continuous development and additions to our software and features. And of course, everything is UK based for our tech support and web-based support. So, just as I finish, these are examples of companies that are using our software to design different items. I know that Tony Holohan there of O'Dwyer's was the retaining walls he got initially, and he was most pleased with the speed at which he could design and the cost savings he could make in his materials using the retaining walls. And finally, if you do want to get a free trial of the retaining walls, just go to the website. If you have any more questions, just fire them through to help@masterseries.com. But if I go to the website here for you, and it's just popped up on the other screen, here we go. And luckily for me, it was on retaining walls. But you're into the website. You can obviously go down to the bottom and say 30-day trial, try now. But if it's only retaining walls you're after, just go straight to the retaining walls button, click on retaining walls, read the beautiful information, and then just say request trial, and that will clearly and succinctly let you fill in your information very simply to get your free trial. And if you do want a personal demo to show 1 or 2 of the items, again you can request that, and myself or one of my colleagues will be more than happy to show you how the software works. So, ladies, gentlemen, everybody, I am going to say thank you very much now for attending.